Hello, this is Eric from UNC Charlotte. Mutex and condition variables are the basis on which all shared memory programming is built. However, they can be hard to use because of their low-level semantic. Today, we will see that we can bring higher-level thinking to shared memory programming by introducing concurrent data structures. To be useful, these data structures are built to have semantics that are useful in a parallel context. Finally, we will discuss how to synchronize the data structures to maximize their performance. When a basic data structure, say a set, is shared across multiple threads, simply operating on the set will lead to race conditions. A common strategy is to associate a mutex with the set to protect the parallel operations. This poses a classic software engineering problem. If we forget once to lock the mutex before accessing the set, a subtle race condition will sneak in the codebase, and it could be particularly difficult to identify during quality assurance or in production. A common software engineering solution is to create a new type where all operations are thread-safe. A simple implementation would be to properly log the access inside all the functions of the object. This is a very common strategy, and it is the primary difference between vectors and ArrayList in Java. Ensuring that each function is atomic does not necessarily protect from all race conditions. The application could need to make multiple calls to the data structure that need to be atomic for the application to be correct. For instance, in SQL, a transaction is granted a serial view of the database even if multiple transactions are operating concurrently. So, if a transaction accesses a table twice, the second access should have data consistent with the first access. Still, having thread-safe objects is an important tool in removing race conditions from applications. But simply locking an object is not enough to provide the semantics needed by parallel applications. Think of a producer-consumer system. Producers will push data in the queue, while consumers will pull data from the queue. Because the producers and consumers could operate at a very different rate, the operations push and pop need to be somewhat redesigned. A consumer that pops data from the shared queue will want to wait on the queue if no data is available. So the pop operation should probably wait on new data being pushed into the queue. In this code, the pop operation waits if the queue is empty, and the push operation will notify the condition variable to awaken one of the threads that may be waiting in the pop operation. While pop will block if the queue is empty, this poses a new problem. This semantic for pop assumes that the calling thread knows that something will eventually be pushed onto the queue. If the thread does not know when to stop popping, it will eventually fall asleep and will never be woken up. There are many ways to solve this problem. They all shift the semantic of the blocking queue to some extent. The most common approach is to have the pop function have two different exit conditions. One is for when an object has successfully been popped, and the other is for when the queue will never have another object. Here, the pop function returns a boolean which indicates which condition happened, but we could also throw an exception in the rare case. The all-done function now enables to indicate that no more objects will be pushed into the queue. Depending on what the application needs, the semantic of the queue can be adjusted. For instance, it is common for concurrent queues to define a maximum size for the queue. And if the queue is full, all pushes become blocking. The simple strategy to make an object concurrent is to globally lock that particular object. It is a reasonable first draft approach, but while the object can be used in a parallel context, the operations to the object cannot be parallel. Handel's law informs us that any point of serialization can cause massive loss of parallel performance. But if we know the data structure more precisely, we may be able to design the data structure to be parallel. Let's consider the case of a dictionary. If we know that the dictionary is implemented using a hash table using OpenHashing, then we can do better. With OpenHashing, the data structure is composed of multiple buckets. A key-value pair would always be stored in the bucket that is indicated by a call to hash of key. That bucket is structured as a linked list, and as such, adding a key value pair essentially adds a link in the hash of key bucket. Let's think of how we could make this more parallel. Hash is certainly a reentrant function, so as long as two threads are not editing the same bucket, they can actually work at the same time. We could have individual locks for each bucket. It would be very unlikely that two threads would ever take the same lock, and as such, the data structure would be very parallel. Typically, a hash table is configured to have about as many buckets as objects stored. Think of the hash table that would do analysis on Wikipedia pages. That hash table would have about 53 million Wikipedia pages in. So that's about 53 million locks. The cost of initializing these locks could become too high, assuming that the kernel even lets you initialize that many locks. Such a high number of locks is completely unnecessary. The system is unlikely to run 53 million threads at the same time anyway. A common strategy is to oversubscribe the locks by having multiple buckets share the same lock. As long as there are enough locks, it will be unlikely to have multiple threads accessing the same lock, and that would reduce the number of locks to manage. How many locks should we have? The birthday paradox provides a theoretical framework, and while you can look into the math, having a number of locks proportional to the square of the number of threads seems to be reasonable. Many data structures can be adapted to be more parallel. Let's look at a binary search tree, for instance. In a binary search tree, the keys are organized in a binary tree so that each node puts all the values smaller than the key on the left and all the values larger on the right. All operations will traverse the tree by asking at each node whether we are done, whether to go left, or whether to go right. The coarse locking strategy is to have only a single lock for the entire tree. A fine-grained strategy would have one lock for each node of the tree. For most operations, the coarse-grained strategy would hold a single lock for theta of depth time. The fine-grained strategy would hold theta of depth locks, but each lock would only be held for big O of 1 time. One could also develop hybrid strategies where not all nodes have their own locks, but locks are held by a node and a few levels down. That would decrease the number of locks to take, but increase the amount of time each lock would be held. To avoid contention on the data structure, another strategy is to have each thread manage its own data structure. Let's think of a set. Each thread would be able to work on its own set without requiring any locks. Though the application needs a single set at the end, so there would be an overhead to pay in order to merge the different sets. Also, that strategy can only be correct if the application has a phase where you add data in the set without ever querying it. If the application cannot support a multiple thread semantic, then the application would be incorrect. Another strategy would be to delay some of the insertions and perform all the operations at once. That would decrease the number of times we need to tag the lock, and it would remove the need for a merge operation. But overall, one would still need to hold the locks for about as much time. We could gain some efficiency by performing batched operation, but probably not much. This strategy enables the threads to access the data in the shared data structure, but the data could be slightly out of date, and the application would need to be correct, even with that batched semantic. In this video, we saw that we probably don't want to use mutexes and condition variables directly in application codes. In some cases, we can push the synchronization logic into data structures that can be made concurrent and parallel. However, the question becomes, what are the parallel semantics that are needed for the application to be correct? Once we know what these semantics are, we can go about implementing these data structures to provide the highest performance.